Hi, this is my research paper presentation for BIOE5820 Biomaterials with Professor Timothy Lannin. My project is optimizing power generating artificial organs for power generation and against the foreign body response. Quick roadmap of the presentation. We'll start with the abstract, move on to motivation, background, current state-of-the-art technologies, then go to my strategy and approach, my proposed strategy and approach, and then we'll end with the summary and conclusion. So the main problem I'm trying to solve with my research proposal is the fact that electronic medical implants such as pacemakers or implantable cardioverter defibrillators often need to be surgically replaced. Um, over the past decade, we've seen a significant increase in biocompatibility, longevity, and reliability in implantable medical devices across the board. But supplying power for enough time and at a sufficient power level is the largest remaining challenge, and research regarding that has largely lagged behind other research concerning implantable medical devices. And as the number of people with similar devices grows, finding efficient ways to power them is essential. Just as a quick example, about 600,000 new pacemakers are implanted every year in the world. And according to the American Heart Association, the number of people living with heart failure in the United States is expected to increase from 6.5 million in 2014 to 8 million by 2030. This shows the necessity for a better power source as soon as possible. There's a lot of solutions that are being researched and investigated right now, but none of them have been proven to be a perfect solution. And surgically replacing implantable medical devices every time they die significantly increases the risk of complications for those that are affected and is also just an uncomfortable procedure. So my research aims to create an artificial organ that generates power using existing concentration gradients within the body and optimizing that artificial organ against the forward body reaction. The inspiration for this project actually came from electric eels, which have specialized electric organs that are able to generate electric discharges using ionic gradients. So a quick review. Um, the basic trick for power generation in electric eels is pretty much similar in all animals. So cells move sodium and potassium in opposite directions across a membrane that kind of works like an insulator. It separates the sodium from the potassium, which creates an electric potential with a voltage between about -30 and -90 millivolts. So with this kind of power, cells can communicate with nearby cells, but it's not enough to power something like a pacemaker. So the thing with eels is they have an organ that can create up to 600 volts potential, so it's about 60,000 more powerful than the one created by our neurons. So what happens is it clusters a bunch of electrocyte cells into several thousand electroplates, and each electrocyte generates about 100 millivolts each. And that all comes together to create the discharge that electric eels are known for. Background and current state-of-the-art technologies. So like I was saying, implantable medical devices provide both valuable physiological information and treatment in humans for a vast variety of applications, including medical diagnoses, prognoses, therapeutic applications, biological science studies. As you can see here, there's a vast variety of implantable medical devices and what they're used for. This is just a few examples, like I mentioned pacemakers and ICDs earlier, but there's also like insulin pumps, cochlear implants for hearing issues, things like that. And so my proposal uses super broad quantitative physiology concepts, which I got into a little bit with the eel, to analyze the power generation portion of the project, and then broad chemistry and biology concepts to optimize the artificial organ against the foreign body response to make sure there's no negative effects from having this organ placed inside of your body. The proposed strategy and approach. So my proposed strategy and approach breaks down my research project into 3 separate experiments. So the first experiment will focus on optimizing the membrane material used for the artificial organ. So this membrane will be placed inside the body to utilize existing concentration gradients similar to what an electric eel does to generate power for these implantable medical devices. So the overall aim is to find an ion selective membrane that's able to maximize the selective transport of protons over other cations, which will thereby maximize power generation. So in order to do this, the experiment would have different ion selective membranes placed in a concentration gradient that imitates that of a human body. and then we will observe how much electric power that each of those membranes is able to generate. So my hypothesis with that is that a hydrogel or a stacked hydrogel, some type of permeable hydrogel, will perform better than any other membranes, any porous membranes, solid membranes, nanocomposites. It seems as if the current research regarding any project similar to this has that as a result. And then experiment 2 will focus on optimizing the membrane material against the human body's foreign body response to make sure there's no negative adverse effects from placing this organ inside a body. So the most promising material that you acquire from experiment 1 will be utilized, and then just a quick potential approach is by using polymer brushes, specifically a polyoligoethylene glycol methacrylate or polyoegma. So polymer brushes are polymer chains that are grafted onto a substrate and they extend perpendicular to the surface, so they resemble sort of like a brush, hence what they're known as polymer brushes. But polyoegma brushes are known for their excellent biocompatibility. They've been shown to reduce protein adsorption, cell adhesion, which are two huge factors in the foreign body response. Research has shown that they reverse anticoagulant activity. There's minimal immune response. So that's just a potential idea. There's a lot of ways you can minimize the foreign body response, but that's a potential one to put in. And I've included a quick diagram here of polyoegma and its structure. And then experiment 3, the last one, will focus on implantation and long-term testing of the optimized membrane. So this will be the optimized membrane you found from experiment 1 with whatever solution you found to minimize the foreign body response in experiment 2 combined, and then implanted in, like mice models, living models, to make sure there's no negative effects. They'll be monitored. The animals will be monitored for signs of inflammation, fibrosis, implant failure, and then the power output will also be measured to make sure that it would provide enough power to be a valid solution to this problem. We'll move to the summary and conclusion. My main research proposal is an electric eel-inspired artificial organ that aims to generate power from existing or concentration gradients in the human body in order to power implantable medical devices, as well as minimizing the foreign body response to implanted materials, specifically the artificial organ that would generate this power. So I just went over the experiments, and the expected outcomes of these research and these experiments will provide super valuable information on the long-term safety and efficacy of this optimized membrane that you would discover, which could have significant implications for the development of more effective and reliable implantable medical devices in the future. And yeah. Thank you for taking the time to listen. If you have any questions, please let me know.